today we are glad to host Kartik, who is a second-year PhD student supervised by Prof. Surajan Kumar at Georgia Tech, and he'll be presenting the paper Representation Learning Continuous Time Dynamic Sign Graphs. And and do you prefer us to ask questions during the presentation or afterwards?
During is fine, yeah, whenever.
Okay, so you can start sharing your screen and let's get started.
Can you see my screen? Oh, no, I guess. Can you see my screen? Anyone?
Yes. Yeah.
Yes, we can.
Should I start? I guess.
Yeah, please go ahead.
Yes.
Okay, thank you for the introduction. And today I will be presenting this work. Thank you for the invitation as well. As mentioned, this work is representation learning and continuous time dynamic sign networks. And this work is under review right now. But yeah, I mean, this is done with these collaborators, and I would be presenting it in detail now. So what do we mean by dynamic sign networks? It's basically like characterized by two features. One is like dynamic, the other is signed. So links can appear or disappear at any point in time here between any pair of nodes. And the second feature is each link is signed. That is, the sign of the link represents a positive or a negative relationship between the nodes. And we study both these features together. And basically, we study signed relationships that evolve over time. So what are the applications of such a domain of dynamic sign networks? Multiple applications can be found. One would be to study and model the evolution of polarization or toxicity in online platforms, where people can interact with each other both positively and negatively. And this interaction evolves temporally, and we would like to study how the toxicity is spread in these platforms, or how the platforms become polarized based on their online discussions. The second application is also that it can help us model consumers' attitude towards a product, because in the future, because consumer has like signed beliefs towards a product, can like the product or dislike the product, and we would like to know in the future, based on these likes and dislikes as a bipartite network, if we can predict what would be his attitude towards a product in the future. Also, another application would be to preemptively find fraudulent users in rating platforms, as fraud detection is itself a field in itself. And in rating platforms, we have assigned relationships between users, and we would like to know if we can find which user is fraudulent. And even to predict the dynamics of relationships between countries, because countries can have signed relationships as well, and these relationships can evolve over time. And this is like a broad, very ambitious thing here, but maybe to even predict the ongoing war before its time, because we can predict it well ahead of its time if data is good, if the model is good, to predict the signed relationships. And yeah, based on these applications, you'll see how we can model, and there can be like other applications as well. First, let's get some background into, let's say, the sign networks. And sign networks, as the name suggests, have positive and negative links. where a positive link represents a support or friend kind of relationship, and a negative link represents a negative relationship, which is to oppose and an enmity relationship. So by definition, positive links are thus homophilous because similar kinds of nodes would have a positive relationship between each other. They are likely to have, while a negative link would be formed between two nodes which are different, and therefore these links would be heterophilous in nature. And this is a very important point because this makes them very different from a normal network, where the links would be likely to be homophilous only.
Just a quick question.
Uh-huh.
How about like neutral links?
Sorry?
How about like neutral links? So I don't have an opinion on the product. So
Mhm.
like a rating of 3 out of 5, for example.
Right. So in this work, like we don't consider neutral links, but neutral links can also be considered. And I guess we then get like a gradient of relationships from negative to going towards the positive. And we do consider one task which tries to learn this gradient or the signed edge weight. But yeah, I mean, still it's in the future works that to consider
Okay.
how we can predict. Yeah.
Thanks.
Cool. Yeah, feel free to interrupt me. I would be happy to take any questions. Cool. So as we said, there is like a different structure in the signed network. And in fact, social studies, social works have studied this phenomenon a lot, this kind of network a lot. And they have found that signed relationships tend to have a definite structure. In particular, the triads in a signed network tend to be balanced, by which I mean that there would be, in each triad, there would be an even number of negative edges. Or in more colloquial fashion, this means that a friend of a friend is likely to be a friend, and a friend of an enemy is likely to be an enemy. So if we think like here, so 3, 2 have 2 is a friend of 3, but 3 is a friend, and 3 is an enemy of 1. So 1 and 2 are likely to be enemies as well. So this kind of balanced triads are likely to occur more in a signed network than unbalanced triads. And this kind of structure is there in real world signed networks. And a good model should kind of exploit this would be the expectation. So unbalanced theory has indeed inspired representation learning for static signed networks. And in particular, we can see here the signed GCN model. Because what it does is it forms k-hop friends and enemies following the balance theory. So for example, if the node is I, then at a second hop, if it's like an enemy of an enemy, if there is like a 2 negative relationships at the second hop neighbor, then it would be likely to be a friend. I mean, kind of like there would be in each, like in different hops, there would be a balanced triads being formed. Even though there is no edge as such, it would try to form balanced triads and form like friend of a friend is a friend and friend of an enemy is an enemy. And therefore, it suggests like even at second hop, there can be a different, there can be a friend and enemy, even though there is no direct link between the two between the two nodes. So it forms these friends and enemies, or what it calls like suggested friends and suggested enemies. And then it learns 2 embeddings by aggregating from friends and enemies separately. So all the friends in k-hop neighbors would be aggregated once, and then all the enemies in the k-hop neighbors would be separate, aggregated differently. And these would form 2 different embeddings. Yeah, so this is like a basic idea, and we would also exploit it in some way.
So if I understand correctly, just to clarify a bit, so essentially, if you want to predict the link from a node A to a node U to V, where U to V have a path, and then you just do the multiplication on the sign, and that will tell you essentially if it's a friend or an enemy, right? Kind of.
Right. Yeah. So if you like multiply it, then it would.
If you have like minus times minus,
Yes.
then you have a positive. Now,
Yes.
if you have a minus times positive, then you still have a minus,
Right. Yeah.
right? So
Yes.
kind of like doing that operation. Okay, thanks.
Yep. Exactly. And this can be extended to like multiple hops as well, doing this multiplication, and that's what they do as well, sort of. Yeah, so it's kind of like extension of the balanced triads, which is only for 2-hop. This can be extended to multiple hops as well. Yes, doing this even number of negatives in a multiplication series. Yes. Okay. Yes. Another background that we would like to give or have here would be about dynamic networks, which I guess would be more familiar with the group. And I would just say that here links typically like unsigned and homogeneous are considered, and they appear or disappear in real time. And therefore, like a temporal order exists between links in a graph structure. In addition to, there is a link structure or which nodes are linked to which other nodes, but there is also a temporal order between these links. And temporal graph networks is one of the state-of-the-art model to learn such representations for dynamic graphs. And it follows these steps, and I would go over them briefly, very briefly actually. So first, there are like a few interactions in a temporal order. They would consider in temporal order, patch them once, and then encode these interactions using the existing embeddings, update these memories, so to say, or representations, and then propagate to long-term neighbors so that the other nodes which are not updated would also get updated, and then update these embeddings again. So this kind of like very briefly how what temporal graph networks does and represent does represent the links or nodes in a temporal manner. And I would also go over this in. So if there are any questions, you can ask them as well. Okay, so this is the background that we need. And we have seen like dynamic unsigned GNNs and static signed GNNs. So our problem here would be to combine these two and see what if links are both signed and are dynamic, so appear or disappear in continuous times. So each of the links has a sign associated with them and can appear or disappear in different points in time. The research question we pose is, what is the most effective way to represent temporally evolving sign links? Because you would like to encode this, and what would be the effective way to do that? Some of the challenges are there to do this, and this is what makes them different from a trivial doing it in a feature, doing it as a additional feature. And one first challenge would be temporal awareness. So representations must be time aware and model the evolution of the interactions, because there is a time information in our data. The second requirement or second challenge for representing dynamic sign network would be that the representations must not remain idle, even in the absence of interactions, because lest they would become stale with respect to the other changes in the graphs embeddings or in the node embeddings elsewhere. And they should be up to date with the how the graph has evolved so far. And the third challenge is sign awareness, that representations must be aware of the higher order organization of the sign structure, such as the balance theory that we have just discussed. Existing works fail to address all these challenges. in a complete manner. So we can see that static signed GNNs would be sign aware, but not temporally aware, or would address staleness. On the other hand, dynamic unsigned GNNs would be temporally aware and would handle staleness, but would not be sign aware. And our model, SEMBA, is an attempt to fulfill this requirement of addressing all these challenges at the same time. Right. I can stop here if there are any questions.
Just one question. What's the difference between temporal awareness and staleness?
Yeah. So by temporal awareness, I mean that the representations consider this temporal order between the links, or would model the evolution. So if a link is coming at time 0.9, let's say, then that has there's an order between the links. So 0.1 appears before 0.9, and this should influence how the embeddings are evolved, or how the representations are formed. But staleness is a slightly different concept. I think it comes more out of the how these representations are made or implemented, because these representations typically how these representations would be learned would be that if an interaction happens, then not the whole graph is not, or whole graph, all the node embeddings would not be changed, but only the embeddings of the endpoints would be changed, right? But this would make the embeddings of the other nodes kind of not stale, basically, like they're not updated according to these new embeddings of their neighbors. So
So
yeah,
it's more like how we update the embeddings, where
right.
the temporal awareness, we are more likely interested in the order. Okay.
Yeah, because in continuous time, it's not feasible to update the whole graph at each point in time, because these, yeah.
Yeah, that's right. Thank you.
I have a question.
Uh-huh.
For temporal awareness, does it mean that actually for static network because it lacks of temporal awareness, does it mean that once it observes there is a interaction, or it observes there's no interaction, you will assume for the indefinite time the interaction will be static as the time it observes?
Sorry, what was the question?
Because you say that the static signed network does not have the temporal awareness.
Yes.
So in this case, does it mean that at the moment we observe an interaction, it will assume the static signed network will assume that this interaction will be persistent throughout the modeling period?
Yeah, I think it's more like a modeling or implementation question. So for how we implement like a temporal graph for static signed GNNs or for experiments is typically just you taking the accumulated graph, remove all the timestamps from the links as an information, and then train on this accumulated graph. So for example, if the training is done until timestamp t, then the whole graph is considered. Yeah, I mean, whatever the links is, we accumulate them on top of each other, and then we consider that static network to train the network, to train the signed chain. Yeah.
Thank you. And for the staleness, because you're saying that we should consider the update in the absence of direct interaction. So in this case, if we have an indirect interaction, like what you mean, a friend is a friend, like what we are talking about for the balance theory. So are we also consider this type of interaction where it's not direct?
So technically, like all interactions are direct. What I mean by direct is directly to that node. So as I said earlier, typically only the node representations of the interactions of the nodes that are interacting with in that interaction are updated, and not the node or not the representations of any other node. So, but we still want to update those representations which are not directly involved in that interaction. Otherwise, they would become stale with respect to these new interactions.
Yeah.
So this is not like associated with what I mean by an indirect interaction or like this higher order organization, because that higher order organization is just it's not really an interaction, but more like a observation or a prior, if you want to call it, that networks tend to be formed like this. They may not. So interactions are still like 1, 2, 2, 3, or 1, 3. But we still want to exploit because, and why do we want to exploit is because we don't have enough negative links to learn this prior from the data itself. So we want to exploit it in the model itself as an inductive bias. So yeah.
Thank you.
Does that make sense? Yeah, cool.
One question related to this. So in this prior work on sign graphs, you said you're given some links, positive and negative, and then you infer some extra links based on this balance theory. Are the links that you infer, are they treated the same way as the actual links that you know for sure? Because maybe you're less certain about them. So
again, I think maybe I misspoke, or maybe there's a misunderstanding. We don't infer the links directly from the balance theory. We don't say that if there is a positive link, then there would be a positive link here. Yeah, we don't consider like that. Rather, we say that, so for example, if there was no sign, then all these at the 2-hop or at the second circle, all these nodes would be considered the same. But since there is a sign, we want to differentiate these nodes in some sense. So how can we differentiate? It's basically like if there is a negative and a positive, if the path from this node in the outer circle to the central node is with an even number of negative links, then they would be different than the those nodes with the path with which have a path with an odd number of negative links. And this is informed due to the balance theory, because an even number of negative links mean there would be that node has kind of a friendship relationship with the central node. So it's just that they would be considered differently. So in the learning process, those embeddings would be aggregated in one way, and then so red nodes would be would message pass in 1-to-1 representation, and the blue nodes would message pass in another representation. So at the central node, there would be 2 different representations learned. Yeah, and then they would be concatenated to learn in an end-to-end manner. Does that make sense?
Yeah, thanks.
Cool. Okay. If there are no more questions, I can jump to this. So in this work, we present Simba, and it's kind of, you can think of it exploiting best of both worlds, static signed and dynamic unsigned networks. Simba stands for signed link evolution using memory modules and balanced aggregation. And we'll see each of these components and what this means in more detail now. So broadly, Simba consists of 3 features, and these are the three features: signed memories, balanced aggregation, and long-term propagation. And these 3 addresses each of the 3 challenges that we have mentioned before. Signed memories basically means that we learn separate memory representations for positive and negative interactions, which is basically like friends and enemies. And this is inspired from what was just discussed with respect to signed GCN, where we also learned 2 different representations for friends and enemies. But those representations were directly embeddings. Here we would learn the memories. Okay, so one difference between a memory and a representation, or memory and an embedding with respect to the TGN model that we are inspired from, is basically that memories are updated only upon an interaction. So upon a direct interaction, if there is an interaction at any point in time, then the memory would be updated. But we still want to inform it from higher order kind of information. And that's how can we inform that based on balance theory is the key question here. And this is done using this thing, what we call as balanced aggregation. So upon there would be one interaction, for example, 2 and 1 interacts at point T1. And these two have memories 2, 2, 1, 1. Or like the positive, negative, and positive, negative memories for each of these nodes. And we want to see which memory would influence which other memory, and based on this interaction, because these memories would be updated, right? So based on balance theory, one idea would be, a very simple idea would be, if there is a positive link, as is there in timestamp T1, then we would update the positive memory with the positive memory, and the positive negative memory with the negative memory. And if there is a negative link, then we do the opposite. We update the positive memory with the negative memory of the other node, and the negative memory with the positive memory of the other node. Why is that? Let's see how that would actually realize the balance theory or enforce the balance theory. So let's say this, at timestamp T1, we influence the positive memory of node 1 is influenced by positive memory of node 2. And at timestamp T2, the positive memory of node 1 influences the negative memory of node 3. But if we now see at different timestamps, it means that the positive memory of node 2 indirectly influences the negative memory of node 3. But and what kind of relationship does 2 and 3 have here? It has like a friend, an enemy of a friend. And the positive memory, which was supposed to represent the friendly relations, is now influencing the negative or the enemies, or basically the enmity kind of relationship for node 3. So in a way, we can say that 2 and 3 have a negative or an enemy kind of relationship in terms of how they are influencing each other indirectly or at multiple timestamps. Does that make sense?
Yes, it does make sense.
Cool, thank you. And similarly, if we now take another timestamp T3, then we can see that the positive memory of node 1 would influence positive memory of node 4. And therefore, indirectly, the positive memory of node 2 influences the positive memory of node 4. And here also, the node 2 and node 4 have a friend of a friend kind of relationship. So therefore, the node 2 and node 4 would also have kind of a friend relationship, and therefore the influence is same. So positive influence is positive. Yep. So this is the basic idea and also the core component of our model. Yeah.
Would you have conflicts sometimes? So let's say from like, because if link production, you are doing node U and V, right? So maybe from like U to V, you think it should be a friend, and then from V to U, there should be an enemy. getting from the two sides are different. So how do you resolve these kind of conflict, or if that's an issue at all? So
so typically, like you're saying that node U to V is a friend while node V to U is a enemy. Is that correct?
yeah, is that possible?
That is possible, but that might so it's unlikely that that would happen at the same time, in a
Okay.
sense. So it
Okay,
can
okay.
happen, yeah.
So the timestamp will kind of sort it out for the most part. Okay.
Yes, the timestamp can sort it out in the sense that at one interaction, when the memories would be updated, they would be updated according to one sign, and then at another timestamp, they would be updated based on the other sign.
So you would have some sort of like override behavior. So like time T3 would be a friend, and then time T4 would be an enemy. Then you will update node embedding to be all be like enemy in that sense.
In a sense, but there would be like a forgetting. So how these memories would be updated would have was not that they would forget whatever has happened before, but they would kind of
Right,
basically
right.
at you. So they would
Okay.
learn based on a sequential learning paradigm.
Thanks.
Cool. Okay. So I can move on, I guess. The third component is the long-term propagation. And this is basically how we deal with staleness. And this is also inspired directly from the T-chain model. So here memories technically, so we learned here some of the memories, the memory representations, but these memories are updated only when there is a direct interaction. And how can we update other representations of nodes which are not directly involved is using this long-term propagation, where we propagate the signed memories or the concatenated signed memories over all the neighbors, not just the neighbors that are formed at this current timestamp, but all the neighbors that are so far formed until this timestamp, to form what are called the embeddings. And the embeddings therefore can maybe updated even if there is no direct interaction. Basically, when there is an interaction, any interaction in any of the neighbors, these embeddings would be updated. Yeah, so that's the basic idea. And yeah, and we implement these three components or these three features in these three these components of the model pipeline. And we can see how we implement them in more detail now, I guess.
Sorry,
yes.
just one question. You mentioned for the long-term propagation, you will concatenate all of the neighbors that have been seen so far. So do you have a threshold on that? Because, for example, different node can have different number of neighbors.
Yes, but it's basically just a GNN layer kind of.
Okay.
So it doesn't matter. Yeah. We'll see how we actually implement it. But yeah. Cool. So okay. If there are no questions, I can move on. So the setup for the training is in this inductive manner, and I would, I guess, we'll all be familiar with this, but I would just go over it in some detail. So it's what we call the temporal batch. So you would update the embeddings or the representations, or we would test the model in this batching manner, where we would update or test the model after a fixed k interactions have happened since the last update. So in continuous time, this is how we do it. Like we fix a number k and wait for k new interactions to happen, and then we batch all these interactions until the last timestamp that it was updated, and then we update the representations again. Just a quick thing. This is different from how we do it in discrete time, where the time interval would be fixed instead of the number of interactions to be fixed. And that's how this would be good.
Do you know if it, how much difference does it make if you change the size of K?
I'm not I'm not sure. Yeah. I guess.
Do you go with the 200 that was set in TGN? The batch size of 200 that's set in TGN, or
Yes,
use a different?
I use the
Okay.
same. Yeah, same batch.
But I think this would actually make difference as well here. If you have a larger batch size, like 1,000 versus 200, then you have more like things to balance in your aggregated graph, in a sense.
Yeah.
But yeah, I'm not clear how performance-wise it was.
Yes, that's true. I don't think we changed it too much. We did some experiments, but it was not changing too much. But I think, yeah, those experiments were not very concrete or comprehensive.
Thanks.
Okay, so the first component is this message generator and aggregating the messages. And we do a small tweak to the TGN model, basically to implement the balanced aggregation part. And so we first have like two different memories, positive and a negative memory, and we would like to generate some messages to update these memories upon an interaction between 1 and 2. So for example, there is an interaction between 1 and 2. We want to update the memories of 1 and 2 based on this interaction. And we would like to enforce the balance theory, as just pointed out. So how we do it is based on the sign of this interaction. So if the sign of the interaction is positive, then we combine memories of the same sign. And if it's negative, we will combine memories of the different sign, as we have seen again. And so these respective memories would be combined in a MLP using the time. And then once it's passed through an MLP, along with the time elapsed since the last time update and at the edge weight, we get a message for each of the nodes. So we get different messages for different nodes based on the time elapsed differences and the memories order. But yeah, we get these messages, and we get like a positive message and a negative message based on where we are looking at, or like which memory is being taken up. So positive memory would generate a positive message, and a negative memory would generate a negative message based on what's the other, what's the sign of the interaction and what's the other memory that we are combining with. Finally, over a batch, we would get these set of signed messages, and we would aggregate them separately by taking the latest message, as is done in the TGN model as well. Okay, and yeah, I guess this is also the major difference that we do in the TGN model, where the difference would be that there would be a single memory representation, and it would be combined up based with it would be combined without regard to any of the sign of the interaction. So no matter what the sign is, the same representation would be used, and they would be combined to generate the messages. Okay.
Excuse me, can I have a question?
Yes.
Apart from your work that has direct applications in social networks, because we have positive and negative interactions between people, if we assume that in an imaginary network there are more than two signs, for example, K colors, K types of colors, 3 colors, and so on, is your approach generalizable to those networks as well?
So I would say no, because this idea of balance makes sense only when there is a polarity of the relationship, a clear polarity of the
Yeah.
relationship. And also in only the social networks of this, typically, because balance theory has been studied only in the, not, I would not say only in the social networks. They have been studied in the, they have studied this theory in other sorts, other networks as well, and have found that it exists. So, but as you said, like for different kinds of relationship or very heterogeneous network where the relationships can have different meanings, then I guess it depends on what the meaning is. So whatever the meaning is of those relationship, if we can exploit, or if we can make a model specific to exploit that relationships. But yeah, I mean, I guess so our model can inspire in some sense that how we can enforce some kind of a higher order organization, or what these relationships would imply in a temporal sense by updating these memories, or this idea that maybe just the memory representations or this module needs to be tweaked according to the new information that has been enforced. So maybe that much, but not directly, I guess.
Okay, thank you.
All right. I guess we have short on time, so quickly, the next component is once these messages are aggregated, we update the memories using this GRU layer as is done in TGN as well. Finally, for the embedding generation, I guess we have talked about this already. We propagate the memories over all the neighbors, and we do this using a graph transformer here. And that's how the different set of neighbors would also be easily included, as was asked, I guess, because we are using a GNN kind of network. And then and this would also avoid staleness, because a node's embedding would be updated even if there is no direct interaction. Okay. So, and yeah, so this summarizes our model, Semba. And yeah, let's see the experiments. Yeah, and I guess this is a major contribution of the work as well, because this setting is different, a new setting. We need to come up with different tasks as well. And the first task that we consider is the typical all familiar dynamic link prediction task. We call it dynamic link existence prediction, to predict whether U and V will be connected in the future. And these connection would be any sign, if there would be a link or not. The second task that we consider is dynamic link sign prediction, where we predict the sign of the link between U and V in the future. So this would be, we know that U and V would be connected. We now want to predict what is the sign between U and V. Is it positive or is it negative, basically? The next task basically combines the two tasks, the two previous tasks. And as a 3-class prediction, we would like to predict if there would be a positive, negative, or a no link between U and V in the future. So we predict if there would be a link between U and V in the future, and if there would be, then what is the sign of that link? And this we call as dynamic link signed existence prediction. The last task that we consider is a regression task, where we predict the signed edge weight of the link. And this is what was asked in the earlier as well, like what would be the gradient of this relationship from -10 to, let's say, +10, where 0 would also be included, actually. So there could be some neutral links. We will see how it fares, but yeah, that kind of gradient between the relationship would also be predicted. Yeah. So these three of these 4 tasks are new, and I guess this is also an important contribution. Okay. So we use 4. Was there a question?
Yes, sorry about that. Wouldn't isn't it the first and second one, or like the third task is the combination of the first two? That's how I could.
Yes, but so the first 2 tasks would be just a binary classification. The third task is 3-class prediction, 3-class classification.
Oh yeah.
Yeah. So we do it like in the same. We can do first and then do it in a pipeline. Like if we first predict whether there would be a link or not, and if there is a link, then we predict. But this requires training for 2 different 2 tasks, 2 different models, so to say. But the third task trains just one model to predict both
Mhm.
2 tasks.
Thank you.
Okay. Yeah. So we use 4 different data sets. These are publicly available, and you can see they have different time scales, different number of interactions, and some of the few observations are that there are very few negative edges. So less than 25% across all the networks. And this is what I was hinting at when I said that we would like to enforce some kind of inductive biases, because the data is not enough to learn this kind of structure on its own. So for example, enemy of a friend is an enemy, this kind of relationship. The data should be enough to learn this, but since there are very few enemies, it might not be. So that's one important observation. And the second observation is that over 80% of the triads are balanced. So these are social networks, as was pointed out, as I guess not clear, but yeah, these are social networks, and they have this balance theory is there in these networks. So unbalanced triangles are just very few, like less than 20% are unbalanced. Okay, I guess from the baselines, we use GCN, SGCN, as is pointed out. SciGAT is just SGCN, but with some tweaks like using GAT and other things. Dynamic unsigned, we used the normal TGN model. We also consider this SGC LSTM network. It's inspired from another work, which is in this direction of dynamic signed networks, representation learning, but it's for an non-inductive and uses random walk and other things. So we extended to use this SGCN, followed by an LSTM, and we encode the graphs using this SGCN and then pass them through a LSTM sequence. So it's a discrete time model, but it can be applied in an inductive manner. Okay. So the first task, we can see Samba matches the performance of TGN and this dynamic link existence prediction task. But we can also see that both the models give very high numbers, and like 99% on F1 and EURC. So there's very little room for improvement anyway. But we can see that Samba does not, even though it like uses this sign as an information, it does not do it by losing out on the standard task of dynamic link existence prediction. The second task, which is specific to signs or sign networks, is dynamic link sign prediction, where the task is to predict the signs. And it's a little harder, and we can see that the performance is not like 99%. It's not doing as that good, all of the models, but we can see that Samba outperforms all the models by a fair margin, giving an improvement of up to 80% in the F1 scores. So TGN performs like poorly on this task for opinions, PKRFA and others, and we can see that Semba does pretty good.
Just a quick question. You mentioned the class imbalance problem with the positive and negative links.
Yeah.
So in this case, if I have a very dumb baseline that just predicts everything as positive edge, how much is it going to perform? Do you have a rough idea?
So
What would be the number?
GCN basically predicts 1 every time.
Okay.
Because like it's unsigned, it does not considers the signed, it just considers, and I mean, we also saw it in the results that, so AUROC being 0.5 and then F1 being 0. So it's like a hint that it's predicting just the characters. Yeah.
I see.
Yeah, so I guess TGN is an indication of what we can learn just from the data. And Semba uses this inductive bias of balance triads in its learning, and SciGAT and SGCN just uses the this kind of balance triads, and GCN does not use anything, so it's like that kind of framework. Okay, and we can see that there is a significant improvement by using Semba. Okay, another task is the dynamic link signed existence prediction. And there are like 3 classes now, and we do different aggregations of the F1 measures: F1 weighted, F1 macro F1, and micro F1, which is the accuracy. And we can see that Semba outperforms the baselines in this case as well. And yeah, I mean, we can see that there is a improvement and across different measures. So it's an indication that Semba or learning or including these signs in the learning process helps in this prediction tasks. However, the last task that we wanted to consider was dynamic link signed weight prediction, but we realized that it's a tougher task. First of all, it's a regression task, and we know there is a bit of research going on in how to do best on a regression task using GNNs, and it's a slightly non-trivial task. Cannot be just used like but we do it rather trivially. We just train using our MSE loss and predict, but we do see that none of the models do good in a sense. The R square is really low, and yeah, and this leaves like and Semba just matches the best performance as such, but this leaves a lot of room for future works in this direction.
Yeah.
Finally, was there a question?
Yes. For this specifically, so actually, like recently, me and Pharma have been running some experiments for edge regression as well on temporal graph. In general, it's very difficult for the methods to do well, even compared to simple baselines that are non-learning based, like just like predicting the last weight that you see for this link in the past, something like that. And so one technical detail: do you still train with the negative sampling from the TGN? Because in TGN they train with positive and negative sampling.
But this, I guess, is just like signed weight. So no, I don't think we do. We just use like RMSE on the class, on the labels or on the weights.
And do you normalize the weights?
Yeah. I mean, I think so. Or actually, I don't know. I don't think we do. We just use like -10 to +10. So we just use -10 to +10. That's yeah. I guess like different normalizations can also help if like a min-max or normalized or using a normal distribution in a sense. Yeah, I guess so. But maybe those kinds of innovations might be it's like those simple tweaks might change the numbers, but a simple or a straightforward implementation was not giving good performance, I guess.
Yeah. Thanks.
Thanks for the insights. Yeah, we'll try that. All right. I guess quickly, we also tried transductive versus inductive setting. So this is for the 3-class prediction. Transductive means there is no new nodes in the test set. Inductive means both nodes are new in the test set. And we would like to see if the Semba is doing good in both these settings and not just favoring one of them. And we do see that there is consistent gains in both these settings. So there is like, except for the last column that is still bizarre, but we do see that there is a, yeah, I mean, there are significant gains in both inductive and transductive settings for Semba. But we do see that there is, interestingly, SGCN performs good on opinions and for inductive setting, which was very clear, which was very peculiar, because SGCN is not a temporal model, and it's like for an inductive case where both nodes are new, it's not clear why that would happen. I mean, it can happen because it still uses the node features, if there are any, or if it can learn during the test set itself, or overfit during the test set itself, in a sense that we do evaluate in an inductive manner as well. So there are some reasons, but I guess you can look into the paper for more such questions, I guess. Yeah.
So yeah, we are at the end of the hour here, so we can quickly wrap up, but just one quick comment on what you were saying. Is it possible that the SGCN is, because you have everything collapsed into one graph, it actually have more global information to make better link, like sign prediction particularly for the opinions, because in your case, you are doing mini batching, right? So you have limited context, well, direct context besides the memory, right? While the opinions, you directly have the edges in the entire graph for you to do inference. So it might be that helps with the performance, and that's my intuition, but I don't know if that's correct.
Yeah, that could be possible indeed, because we do see like TGN does not do as good for inductive settings for both these WikiRF and opinions. So it is interesting, and it could be that the global information is useful here. Cool. I guess I will just wrap up very quickly. The final ablation is like on just removing one of the components, and we see that memory modules are the most important, drops the performance the most. But we can also see that balanced aggregation, which is the core component of our model, can be as important as the embedding module, which was for the staleness, which was toward staleness. Because for opinions or for WikiRFA, we do see that balanced aggregation also gives a very stark reduction in the performance. Okay. Yeah, let me conclude. I guess we do consider novel problem for predicting the sign structure of temporally evolving links. And to this end, we present this novel model to learn effective representations. And we find that our model outperforms the existing baselines on different new dynamic sign tasks. Okay, thank you. I guess there's no time for questions, but I would be happy to take if there are.
Yeah, for the sake of time, so maybe if you have any questions, feel free to read it in the TGL Slack or send an email to Kartik. And thanks so much, everyone, for joining the reading group. And we'll see you all next week.
Thank you very much.
Thank you. See you.